In this video, we're going to do some extra examples of approximating quantities or changes in quantities using a linear approximation and or differentials. So the first one, we want to approximate ln of 1.03. So I gave myself lots of room, so I'm going to do actually both methods. So I'm going to start with the linear approximation. Okay, now remember these are in fact the same. Okay, they're doing the same thing, they just look different. So because I want to approximate ln of 1.03, I want this to be the y value of a function at a specific x value. So what I'm going to, so I want something, so I'm going to use f of x is equal to ln x, okay, because then what I want to approximate is f of 1.03. Okay, so now it's a y value of this function. Okay, so my x value is 1.03. So I want to find a nice point. Okay, something that's close to x equals 1.3, but where I know how to compute ln of it. Okay, and now here I think the best point to use is going to be x equals 1. Okay, it's close to 1.03, and ln of 1, the y value, so f of 1, ln of 1 is 0. Okay, so our nice point is the point, not 0, 1, 1, 0. Okay, so that's our nice point. And we're going to use that to approximate 1.03. Okay, so this is all for both methods. Now for the linear approximation, what we want to do is find the equation of the line tangent to f of x, okay, at our nice point, okay, which is 1, 0, so when x is 1. Okay, and then we're going to plug 1.03 into the tangent line to approximate the y value. Okay, so that's the idea of the method. So we want to find the equation for the tangent line. So that means I want the slope. Okay, so if f of x is ln of x, then f prime of x is 1 over x. Okay, so that means that the slope, m, is f prime of 1, which is going to be 1 over 1, which is 1. So I have a slope of 1 and my point is 1, 0. So my equation for the tangent line is y minus 0 equals 1 times x minus 1. Okay, so I actually just get y equals x minus 1. Okay, so that's my tangent line. So we're going to use this. So that means ln of 1.03, which equals f of 1.03, is approximated by plugging into the tangent line. So I'm going to plug in 1.03 minus 1. Okay, so we get 0.03 as our approximation for ln of 1.03. Oops. Okay, so that's our approximation here. I just want to emphasize, so what I did was to approximate, so the approximation, we're plugging into the tangent line instead of the function. Okay, so that's what we did there. Okay, so that is the linear approximation. Okay, now what we're going to do is try to use differentials. Okay, so we still need f prime of x. So I'm just going to write that. So f prime of x is still 1 over x. Okay, now here our nice point is x equals 1, and our not nice point is x equals 1.03. So to go from the nice to the not nice, that means that my delta x, or my dx, has to be 0.03, because I should have the not nice point equals the nice point plus dx. Okay, so I need to add 0.03. So that's my dx. So that means that dy is f prime at my nice point times the change. Okay, so that is f prime of 1 we know is 1 times the change is 0.03. So dy is 0.03. Okay, now delta y, which we know is the change, the actual change, so it's f of 1.03 minus f of 1. Okay, now this, so if dy approximates delta y, then that means that dy is approximately ln of 1.03 minus ln of 1. So if ln of 1, actually this one is 0, okay, so I don't even need that. So that means here that ln of 1.03 is approximately equal to dy. And we just found that dy is 0.03. So ln of 1.03 is approximately 0.03. Okay, so that would be our approximation of this value. Okay, now if we wanted the actual value, so if we compute ln of 0.03, oh sorry, 1.03. I was wondering what was going on there. We get ln of 1.03 is actually equal 0.029559. Okay, so this is actually a very close, pretty close approximation. Just to compare how close we actually were. Okay, so that's using both each method. Okay, either of them are fine to use. Like I said, I prefer the linear approximation because it just makes more sense to me. It's doing the stuff I've already done. Okay, so let's try another one. Here's sort of a more applied application. So we can use differentials to estimate errors that might occur when we're measuring some sort of physical quantity. Okay, so here, let's say that we're trying to determine the measurement of a spherical ball bearing. Okay, and our measurement, we see that it has a radius of 0.6 millimeters. Okay, so that's pretty small, less than 1 millimeter. And we know that our error in our measurement of the radius is off by, at most, plus or minus 0.015 millimeters. Okay, so that's actually dr dt. Oh, I didn't actually put the question in here. So used to approximate the error in the measurement of the volume, okay, of a spherical ball bearing. That's what I wanted to say. So we're given that dr, or sorry, not dr, delta r, so the amount that we're off by, okay, which this is like our x, so this is dr, is plus or minus 0.015 millimeters. Okay, and what we want to do is we want to approximate delta v. Okay, so this is the error in the volume calculation or measurement. Okay, so if we use our measurement for the radius, it's going to have a different effect on the volume. So for a sphere, the volume is 4/3 pi r cubed. Okay, so delta v is approximately dv. Okay, and dv has formula v prime, so the derivative of our equation at our nice point. This is at our measurement. I'm going to put at our measurement times dr. Okay, so it's f prime of r times dr. Okay, so our measurement r equals our measurement that they gave us. So we measured 0.6 millimeters. Okay, and the dr we said was plus or minus 0.015. So that's how far off our measurement might have been. Okay, so the derivative, so v prime here, is 4 pi r squared, because the 3's are going to cancel. So this is going to be 4 pi times our measurement squared. Okay, now times the amount we could be off by, that's plus or minus 0.015. Okay, so if you compute this, you get plus or minus 0.0679, and this is in millimeters cubed. Okay, so we would estimate the resulting error in the volume measurement to be plus or minus 0.0679 millimeters cubed from the actual volume. Wow, that's messy. From the actual volume. Okay, so the most that we would think that we're off by is plus or minus 0.0679 millimeters cubed.